So our topic for today is the contact process. Our learning objective at the end of this lesson, we should be able to demonstrate knowledge, demonstrate beautiful understanding, and where necessary application of these following ideas. List the raw materials. We should be able to tell the raw materials of contact process. There are 4 stages in this process. We should be able to write the chemical equations for each of the stage. Then there is one of the stage that is a reversible reaction. We should be able to explain the chemistry or the conditions for that reversible stage. Okay, so let's make a start. Our first learning objective, the raw materials. Before then, you want to find out exactly what is contact process, raw materials. What do you think contact process is? Contact process is actually the industrial manufacture of sulfuric acid. Okay, perhaps we might want to write that, but then let's look at the raw materials first. There are 3 key raw materials. You have sulfur, you will need sulfur. If you don't have sulfur, we can actually start with sulfur dioxide. Okay. Another raw material that is necessary is air. Third raw material is water. So your IGCSE might ask you to list 2 raw material for the contact process. Please, you will need to tell us that sulfur and air, or you could choose sulfur and water. Never you say sulfur and sulfur dioxide. You've said one thing. I just said or, not and. Okay, so please don't get it twisted. It's either you have sulfur or you start with sulfur dioxide. Okay, so what is the contact process? Contact process, I've said, is the industrial making of sulfuric acid. So making sulfuric acid industrially is what the contact process is all about. There are many reasons for us to make use of sulfuric acid, very important chemical in the chemical industries. Okay, so we've listed the raw materials. Now let's go to the different stages. Stage 1. What is the first stage? Stage 1. Okay, stage 1 of the contact process. Sulfur, starting with sulfur. Sulfur is burnt. You could say it's roasted or it's burnt in air. Okay, sulfur is burnt in air to form what? To form sulfur dioxide. Okay. So that's stage 1. Sulfur is burnt in air to form sulfur dioxide. You will need to write the equation. We've said sulfur. So you have S, sulfur is solid, plus oxygen. Oxygen is a gas. Please remember, oxygen is coming from air. Air is a mixture, so something in air combines with the sulfur. And when we say burnt, you know, is actually an oxidation reaction. This stage is irreversible to give you sulfur dioxide. Sulfur dioxide is a gas. Please always remember to balance Always remember to balance your equations. Simple equations must always and always be balanced. Okay, so the next stage, stage 2. Stage 2. Stage 2. The sulfur dioxide in stage 1. Sulfur dioxide. Sulfur dioxide is reacted with more air. Sulfur dioxide is reacted. Sulfur dioxide is reacted with more air to produce sulfur trioxide. Sulfur dioxide is made to react with more air to produce sulfur trioxide. Okay, so we need to write the equation. Sulfur dioxide is a gas, is made to react with more air, which is oxygen, gas again, to produce sulfur trioxide. Please note that this stage is reversible. So spend some time here looking at the condition for the reversible products, reversible reaction. This is also a gas at the temperature. Now we need to balance the equation. I told you your simple equations must always and always be balanced. This balances the equation. We have two sulfur and 2 sulfur here. We have 2 times 2 oxygen, so 4 oxygen and 6 oxygen. We have 2 times 3, 6 oxygen. So this stage is reversible. At what temperature will this reaction take place? Now, going by Le Chatelier's principle, your idea of equilibrium, you will know that increasing temperature favor endothermic reaction, reducing temperature favor exothermic reaction. Now, this reaction is exothermic. The forward reaction is exothermic. So the forward reaction is exothermic. So if we increase temperature, what happens? Increasing temperature. If we increase temperature, what happens? It favors the endothermic reaction. It means we will have more of the reactant this way. But that's not our aim. Our aim is to get this, is to get sulfur trioxide. So we need to reduce temperature if we go by Le Chatelier's principle. The shocking thing is that even at this temperature, I mean this reaction, we have to increase temperature for 2 reasons. So let's write the equation again. Sulfur dioxide plus oxygen gas reversibly giving us sulfur trioxide gas at this stage. Equations must be balanced. Now, at what temperature? What's the temperature? Please. The contact process operates at a very high temperature of 450 degrees C. Wow, why would that be? Why would that be when we know that increasing temperature will favor endothermic reaction? Please remember the idea of rate. Rate saves time, and time is money. So increasing the temperature increases rates. Increasing the temperature increases rates. And what? Saves time. Okay? So for cost, we have to increase the temperature. To save cost, we have to increase the temperature so that the reaction will be fast. Now, this reaction also uses a catalyst. It also uses a catalyst. Temperature reaction uses a catalyst. The catalyst is vanadium 5 oxide. So please, this is the name of the compound of the catalyst, and the formula is V2O5. Please don't get it twisted. When IGCSE asks you what's the name, please learn to write the name. Don't miss it with the formula. If they say write the formula, please write this. Write the name, please write this. Okay, so this catalyst cannot work. Catalyst will not work. Vanadium 5 oxide will not work at a lower temperature. So at temperature lower than 450, at temperature lower than 450 degrees C, vanadium 5 oxide will not work. And you know that catalyst will speed up rates. So lowering the temperature will have serious implication to time and our rate of reaction. So because of rate, the temperature is increased. Now, at what pressure will this reaction take place? Going by the Le Chatelier's principle again. So let's look at the pressure again. Pressure for this reaction. What will the pressure be? Let's go back to our equation. This is our equation, reversibly this way. This is the gas. Please, because we are talking about pressure now, we need to include that. That's the gas. Okay. So this is the number of moles here. So we have 2 moles or 2 volume. Here we have 1 mole. Altogether we have 3. Here we have just 2. Okay, so 2 moles. Now, from your equilibrium ideal, you know that increasing pressure always favor the side with fewer volume or moles. Okay, so if we increase the pressure, more of this will be produced. It will increase the yield of sulfur trioxide that we are looking for. But the surprising thing again, this process is loaded with surprises. However, the pressure of the contact process is within 1 to 2 atmosphere. 1 to 2 atmosphere. 1 to 2 atmosphere. Why is that? The simple reason is that at the operating condition, the yield of SO3, sulfur trioxide, is already sufficient. The yield of sulfur trioxide is already sufficient. So if the yield is already sufficient, the problem is Why will we spend so much money to build a material that will withstand high pressure, In other words, we'll be looking for materials that are sturdy, that are hard, that are rigid to withstand high pressure. Okay, so if the yield is already sufficient at the operating condition, then we will not need to spend so much money building materials that are going to be very costly. Okay, please take notes of that. So the pressure of the contact process, pressure used in the contact process is that. So apart from this, there is something else we can do to increase the yield. What can we do to increase the yield? Is the removal of this guy. Okay, removal of this guy. Removal of this guy is what takes us to the next stage. Removal of that guy takes us to the next stage. Okay, so we are on stage 3, removal of SO3, sulfur trioxide, by dissolving in concentrated sulfuric acid. Okay, so this guy comes sulfur dioxide plus oxygen comes into the catalytic converter chamber. Okay, comes into the catalytic converter chamber. You have catalytic bed. And this is let out this way. This is let out that way. So here you have the vanadium oxide pellets. You have the vanadium oxide pellets, and we refer to that as the catalytic bed. Okay, so this is the catalyst. That's the catalyst, and here we say is the catalytic bed. Okay, so sulfur trioxide comes this way and is being removed. It is being removed by dissolving into sulfuric acid. When it's dissolved into sulfuric acid, it forms to form a substance known as toluene. Okay, toluene is an oily liquid. Even sulfuric acid is very oily. Okay, so that's what takes place. So you have your sulfuric SO3 here, SO3 is being taken away by dissolving in sulfuric acid. Now there's a beautiful question you need to ask. First question is that why do we have so many catalytic beds? We have so many catalytic beds to increase the chances of reaction. Okay, so we have so many catalytic beds just because we want no excuses. There are no excuses. Okay, now that's what happened. So we dissolve in sulfuric acid to form toluene. You will need to write the equation for this reaction. So you have SO3, please. SO3 is a gas, and you dissolve in water. Water, we told you water is one of the raw material for this reaction as liquid, and you form oluene. Please, you don't need to bother yourself about the formula of oluene. How many hydrogen here, you write. That way you remember the formula of oluene, how many hydrogen. Sorry, I just made a mistake. We are dissolving it in sulfuric acid, not water. Okay? So we are dissolving SO3 in sulfuric acid, okay, which is SO4, H2SO4. Okay, it's concentrated, so we put liquid if we want to show state symbols. So you don't need to bother yourself about the formula like I was saying. How many hydrogen? It's 2 hydrogen, right? 2. Then sulfur, how many sulfur? 1, 2, right? 2 sulfur. How many oxygen? You have 4 and 3, 7 oxygen. Okay, liquid. This is concentrated and oil. Okay, so oily liquid. That's what we said. Oluene is oily liquid. Okay, so another question somebody will want to ask is that where do we get this sulfuric acid from? The first sulfuric acid that was made, where did you get it from? Students used to ask that question. Now we can actually remove this SO3 by dissolving it in water. 2, if we want, dissolve it in water. If we dissolve it in water, we can actually have our sulfuric acid straight. Okay, we can have our sulfuric acid straight. But stop! Don't do that. Why would I not do that? Because the reaction. Please note why we will not do that. This reaction is extremely exothermic. What that simply means is that it will release serious heat energy that can be dangerous to people who are doing it, can be very, very damaging. So extremely exothermic. It has another side effect. It forms acid mist. It forms acid mist. What that means is that the air around there will just be acid. So breathing this air is breathing sulfuric acid. Now these events, these are very, very dangerous occurrence. You wouldn't want that to happen to your brother who is carrying out the process. Okay, so that's why we will not dissolve in water, rather we dissolve in already made concentrated sulfuric acid. Okay, so let's look at the last stage, stage 4. How do we get our sulfuric acid back from oluene? Stage 4, oluene is dissolved. Oluene is dissolved in water. Stage 4, oluene is dissolved in water to form what? To form what we are looking for, sulfuric acid. Oluene is dissolved in water, and we have our sulfuric acid. Okay, so let's write the equation for each stage. I told you we need to write the equation for each stage. That's your oluene, you know, and we told you it's an oily liquid. You dissolve in water, H2O, sorry, H2O, dissolve in water, H2O, and liquid. Then you have 2 moles of sulfuric acid. This sulfuric acid is about 98% pure. Sulfuric acid made in this fashion is about 98% pure. Okay, so this is the last stage of the contact process. I believe you had a good time. You need these concepts, the equation of each stage, reasons for the conditions in the reversible stage. All of this you need to make your IGCSE look good. Okay, so let's look at our objective again. Are you able to remember the objective? Are you able to list the raw materials? What are the raw materials for the contact process? One, you want to remind me, yes, quickly, you need sulfur or sulfur dioxide. Okay, then you need air. So these things are needed. You also need water. So what we need to do at this stage. Now let's look at equation for stages. Equations for the stages. Stage 1, sulfur S is made to react with oxygen. Oxygen is coming from air, to give you SO2. SO2 is also a gas. Stage 2, your SO2 gas is made to react with more air, oxygen, in a reversible reaction at 450 degrees C, and say 2 atmosphere vanadium 5 oxide as the catalyst to give you SO3 as a gas. Please remember, simple equations must always be balanced. Okay, stage 3, sulfur trioxide. Sulfur trioxide is removed to increase the yield by dissolving in sulfuric acid. Sulfur trioxide as a gas, it's liquid. This stage is not reversible to give you Oluene. And we said you don't have to bother yourself about the formula Oluene. Just remember what is involved in the reactant. Count the number of atoms. Sulfur is 2, S is 2, oxygen 7, to give you a thick, oily liquid called Oluene. Okay, stage 4, we have Oluene being dissolved in water. Oluene, thick liquid, dissolved in H2O, liquid, to give you 2 moles of 98% very, very pure sulfuric acid, liquid. Okay, so that's it for contact process. Just remember all of these points, and you don't have issues with your IGCSE. So I appreciate your time. Thank you for listening. Hope to see you again when we treat uses of sulfur and uses of sulfuric acid and sources of sulfur. Bless you.